bipylon rocket engine. Presenting today is Jack Slayton, Elias Perez, and Austin Morris.
All right, yeah, so this is our presentation related to the simulation that we've created to model our liquid bipylon rocket engine. Something to note for this presentation is that while our actual paper goes pretty in-depth into the numerical methods and driving equations about the simulation, this is going to be a more qualitative overview of the applications of the simulation. Next slide. All right, so a little bit of background of who we are. So we're part of the Tartarus project within the University of Alabama and Huntsville Space Hardware Club. So the Space Hardware Club is a student organization that basically acts as a medium for different aerospace-related projects, meaning they give us lab space and funding for these projects. Right now the club has about 200 members operating 13 different projects across 4 programs. And the Tartarus project that we're part of is operating about 20 students over 3 different sub-teams. The project is related to the development and testing of liquid bipylon rocket engines, and we've been operating since August of 2017. Next slide, please. So this is the engine that we're focusing on today. This is our workhorse engine. This engine was developed and manufactured at the university in 2019. This engine uses nitrous oxide and ethane as the propellants. It operates in a blowdown cycle, so those propellants were chosen for their self-pressurizing characteristics. The primary cooling method for this engine is film cooling, and this engine is designed solely to validate testing hardware and procedures. It's a very poorly performing engine, but it just needs to survive so that we can get that taste out of it. That's why it's the workhorse.
All right. So we already have the intended design values for the workhorse on hand, but we want to make a simulation that maybe will account for non-idealized conditions we'll encounter in tests. So whenever the engine was designed, we might assume a specific initial propellant temperature or an initial fuelage volume, but in reality, we may be targeting an 85% fuelage volume, but we may hit 80 or 90%. In particular, the temperature of the propellant independent before firing is of particular concern because it can very severely affect the vapor pressure of the propellant in the tank, which will affect the self-pressurization quite significantly. So we want to account for that. It also introduces a transient dynamic, so as the tank drains, the fuelage pressure will drop as the propellant expands, vapor often cools in the tank. So we want to make a simulation software or program which could account for the transient effects of tank draining while still accounting for the coupling of each component of the system and the effects that each component has on the state of behavior of the other. So for example, the effect of change pressures on gas flow rate, which in turn will affect the drain rate and therefore the fuelage conditions over time of our propellant tank. And finally, once we have the simulation on hand, in order to make sure that the work we do is still applicable in the future, like we mentioned earlier, the workhorse engine is just a demonstrator. We want to eventually make a flight-ready model or one that is higher performance. In order to do that, we want to basically use the simulation as a tool to help drive the design process of any future engines. So different nozzle designs, different propellant selection, especially different injector layout and orifice sizing. Now, with these requirements, we are going to have to operate within some constraints that are inherent to an undergraduate student program. So all of our work has to be fairly easy to reproduce. The turnover rate for undergraduate projects are infamously high, so any work that we need to do will need to be both applicable to feature an easier to use by anyone who likes to see us and getting less experience than we have. We also want to try and avoid any licensing software, not necessarily because it's inaccessible or particularly expensive. Student licenses are usually too expensive, but rather because if you go and ask a software provider for a license, they'll often give it to you in batches, so then you'll have to go and get more licenses as your team turns over, and you have to bring on more people to replace them. And finally, most notably, we want to make a simulation which is able to support the two-phase dynamics of our system. So selecting nitrous oxide and ethane as both self-pressurizing propellants means that you cannot, as is traditionally done, treat your propellants as liquids, or just liquids, I should say, throughout the system, particularly in the tanks and at the injector orifices. So we want to make sure that any modeling work we do accounts for that effect on the behavior of the system. So the results was a series of scripts and functions developed in MATLAB. We chose MATLAB because, like we said, we wanted something that was accessible to anyone who might come after us. And anyone at the University of Alabama in Huntsville has access to a MATLAB license. So anyone would be able to, theoretically, we'd be able to send them our files, and we'd be able to pick that file and recreate all the math and the work we've done. Also along that line, we tried to select open source plugins for accessibility. So again, we chose CoolProp for our thermal tables, Cantera for our chemical equilibrium analysis. Again, so that way it's easier for anyone who comes after us or anyone else who might want to utilize this tool to simply download these two plugins from MATLAB directly and be able to recreate all of our work. And finally, we wanted to make sure that our model could take our system specs, our design as driving inputs. So in essence, what we did is we wanted it to be so that you would describe what the system looks like to MATLAB, novel dimensions, work sizing, count selection, and conditions. You tell MATLAB what configuration your system is in, what it looks like, and it spits out, this is what we think it'll do as it fires throughout draining. Now, like we said earlier, we're not going to bore you with the, we're going to spare you the actual driving equations. We're going to take a very qualitative look at how we did this. Mostly consisted of compiling existing methods from existing tested research methods from other publications. And then we also developed some numerical models ourselves, mostly for the purpose of taking distinct modeling methods, such as, say, two-phase mass flow rate to the injector with self-pressurizing Euler's pressure and making them work together. The first thing we had to account for was we had to account for two-phase dynamics in the injector. This was simplest. We simply used a model proposed by Dyer. In essence, you can't use the traditional mass flow rate equation. You can't just treat it as a liquid because, well, it's not. You're injecting it as a two-phase mixture. It's about half liquid, half gas. That one was simple enough. It's just a single equation. It gets more complex when you try and model your self-pressurizing Euler's pressure and temperature over time. We used a numerical integration similar in principle to an Euler's method of a model proposed by Tartarus for nitrous oxide self-pressurizing rockets. These two are coupled over time. So the mass flow rate dictated by our injector model then dictates how and dictates our Euler's conditions over time as the tank drains. Finally, once we parameterized our injector and our tank conditions as functions of the system design and of the states of the other components of the system, we want to be able to obtain our lump parameter chamber conditions. So basically the actually interesting part where the fire is. The method we used was developed here. You can, again, I'll try and spare you the details, but you can see a general outline of the logic here in our paper. Similar in principle to a Gauss-Seidel method, we make a simplifying assumption here that the system will relatively quickly converge to a steady state. Therefore, mass flow rate in is about equal to mass flow rate out, and we take we feed our parameterized injector mass flow rate, CROF, feed that to our chemical equilibrium analysis, feed it then to the traditional rocketry 101 nozzle mass flow rate equation, and then iterate until the two equations agree on a particular chamber pressure, chamber temperature, gas properties for a particular time step.
All right. So, in order to find the necessary thermochemical properties of the exhaust in the chamber post-combustion, one has to find some solution to the many chemical reactions and their equilibrium equations present in that chemical reaction within the chamber. So to solve this analytically, one would have to solve a large system of equations corresponding to every single equilibrium equation for every relevant chemical reaction. For high fidelity models, these reactions can number in the hundreds with dozens and dozens of component species. The team did attempt earlier in the process to sort of write our own code to evaluate these equilibrium equations, but we found that the fidelity and the computation time were not sort of up to our standards. So we decided to offload the work to a chemical equilibrium analysis program called Cantera. So the three main reasons we decided to go with Cantera over any other option are that, one, as we've said previously, Cantera is completely open source, so anyone can download it and utilize it with our code or on its own without needing any special license or permissions. Additionally, Cantera is completely integratable and compatible with MATLAB, so pretty much since our entire model is contained within MATLAB, being able to run our chemical equilibrium analysis completely within the script without requiring any sort of human or software interface to combine our calculations is very helpful for computation time and simplicity. And third, Cantera is actually capable of supporting many different reaction mechanisms. So Cantera actually comes bundled with its data a large amount of separate reaction mechanisms that can resolve chemical reactions for many different components in many different situations, and includes a process by which one can convert chemistry or industry standard chemicals files into reaction files it can read and then do chemical equilibrium analysis on completely independently. So this expands basically our propellant choices that we can potentially use essentially arbitrarily as long as these files exist. So using Cantera within our model, we are able to seamlessly and automatically calculate important thermochemical data such as adiabatic flame temperature of the chemical reaction, the ratio of specific heats of the exhaust products, and the gas content of the exhaust products for a variety of mixture ratios and chamber pressures, sort of giving us the versatility we desire with this model, as you can somewhat see by this lovely graph showing sort of the wide ranges of values we can calculate using Cantera. So our actual model utilizes the GRI MEC 3.0 reaction mechanism. This mechanism was developed by Berkeley University for use with natural gas air combustion. The reason we are using it with our particular propellant choice is that by simulating the natural gas air reaction, it actually is capable of simulating pretty much all of the intermediate products that would entail, which include many sort of nitrous compounds such as nitrous oxide or oxidizer, and smaller hydrocarbons such as ethane or fuel. So it's able to simulate the relevant chemical reactions with high fidelity. Now, you have a rocket that is currently firing. That's wonderful. The next step is to make sure it doesn't melt itself in the process. So as stated previously, our rocket utilizes film cooling, also known as boundary layer cooling, in order to prevent the sort of temperature of the walls from exceeding its melting point, so to sort of control thermals within the chamber. So in order to analyze this, a numerical analysis by W.N. Grissom was applied. Pretty much the basis of this analysis is that it computes the temperature and enthalpy of the coolant that is entering the walls of the engine chamber, pretty much by a stepwise numerical integration. It calculates heat transfer between the free stream gas of the combustion chamber and the coolant flow using a correlation of the Stanton number. And using this, it's able to model the coolant heating up initially, then beginning an evaporative phase, sort of a two-phase state, and finally entering a gaseous state where it begins to cool in a less effective manner, but still has an effect. Our model, detailed by W.N. Grissom, also applies for both convective and radiative heat transfer from the combustion chamber. So we are able to actually estimate the radiative heat transfer using empirical correlations for the radiation of water and carbon monoxide within the combustion products to sort of get a complete picture of the heat chamber to the coolant wall. So this allows us to actually calculate the sort of what is called the steady state temperature of the engine wall, as that is the point where we will assume that the temperature at the engine wall is equal to the coolant temperature. So as you can see here, we have sort of a curve representing that. As you can see, we sort of have an asymptotic relationship where it goes up into the mid 2000 Kelvin further down the chamber. This is because we are using a gaseous boundary layer cooling in this instance, which is sort of less effective than a liquid. But for short firing times, this doesn't matter as much because we also have to worry about transient heat transfer. So in order to calculate that, we use a different correlation, the Bart's correlation, which gives us a heat transfer coefficient between the actual coolant and the wall itself. So that will be utilized in another analysis. So in order to study the structural and thermal response of our engine to the stresses of firing, we actually ported our engine model into a different software, SolidWorks, in order to run a finite element analysis on it. So pretty much what this entails is taking our values for conductive and radiative heat transfer at several different axial points within the nozzle, and transferring the Bart's correlation heat transfer coefficients into our FEA simulation, applying them at several different axial lengths of the chamber, and then pretty much from there we are able to simulate the sort of heat buildup in the transient phase of the engine wall, which allows us to sort of see how heat and stresses build up in the engine during firing, allowing us to simulate how long the engine can be fired before the factor of safety becomes too low for safety. We talked a lot about what this model can do, our sort of methods of modeling its behavior and such. Now we need to talk about what this model can actually do for us. So this model is capable of simulating engine firing in both transient and steady state configurations, so for both an engine that is intended to fire for a long period and an engine which is only firing for a short period, or which has its sort of inlet characteristics or chamber characteristics vary during firing. We are able to simulate that. So our models are also able to quickly generate preliminary test data that we can use later empirical hot fire data to sort of test against to verify our engine models. And more importantly for our future sort of engine design, this model is able to very quickly sort of calculate responses to changes in the engine parameters itself. So for instance, we can test the effect of different injector geometries, different propellant combinations, different engine geometries, and stuff like that to greatly accelerate the engine development process.
All right. Now we've already talked about what this model will be able to do for us or for the project. It's all well good, however, it's no good to us unless the simulation has actually been validated. So we have an idea of how our system is supposed to behave, what kind of performance we're going to get out of it during a static fire test, but that's no good unless we know how it actually performs in a static fire test. We want to validate the accuracy of our simulation, not just of the combined simulation, but also each component. So maybe we go on a model which may end up not actually matching the experimental behavior quite as close as we thought it would have, and we may need to swap that out later on. We may also develop empirical correction factors of our own for ethane and nitrous oxide specifically, so that way we may be able to enhance the model, the accuracy of the model later on as we go. But of course, later on down the line, if we want to switch to a different propellant combination, maybe methalox, for example, it wouldn't be applicable, but it would be applicable specifically for ethane and nitrous. So that brings us to the future work that we're going to be undertaking over the next few months. Once we have our validation complete, we'll apply any empirical corrections as appropriate, or we modify the simulation again as appropriate. In order to make our model a little more accessible, we're still working on the GUI, it's still in the works. Right now, all of the skeleton is there, all of the math is there, but that's no good if newer members to the team it's too unwieldy for them to use, or for anyone else who might use our tools. And finally, we also want to implement more reaction mechanisms so that we can support a wider array of propellants. So GRI 30, as Austin said, GRI 30 does support ethane nitrous oxide, but for example, one of the more notable shortcomings of it is that it does not support kerosene, which is a very common propellant that student projects will use. So we want to add support for that. As for the future applications we have for it, right now we're mostly using it for analyzing different test configurations. So what if the propellant enters the tank at a colder temperature than we thought, or it's higher? What if our ullage volume is off? How will that affect it? And then finally, like we said earlier, once we have validated the simulation, we hope to use it to drive the design of future rocket engines. That brings us up to where we are today. Questions from the panel?
We haven't done any testing yet.
It turns out handling propellants, liquid propellants, is logistically very difficult.
Yeah.
Yeah, especially for a bunch of undergrads.
You think you'll be able to do so by the time you guys finish this semester, or following work for next week?
That's going to be work for next year, yes. Right now, what I'm doing is Washington is I'm very much laying the groundwork for people that are going to come after me. I'm trying to make sure that I leave my work in a state that's very easy for someone else to pick up. Actually, for Austin here to pick up, he'll be my successor.
Let me understanding in liquid propellant engines, you either got pressure fed or pump fed. So what your bipropellants is what providing you pressurization.
Yes.
Where you don't have to have a pump, and then you don't have to have some other external means of pressurization.
In essence, yes. So what you'll often see is sometimes you'll see rockets, like let's say if you were using LOX, you would fill your tank about halfway, and then you would have 50% ullage volume would be an inert gas, like nitrogen usually, because it's pretty cheap. And then that inert gas sitting on top is what provides your pressure. With nitrous oxide, the vapor pressure is up to somewhere on the order of about 900 psi. So you can have a higher ullage volume, so that way the vapors coming off of the nitrous can provide ullage pressure in addition to an inert gas usually applied on top of it. So usually what that takes the shape of is you apply a partial pressure of nitrogen in our case up to 800 psi, and then you cut the inert gas feed, and then the amount of the nitrogen in the tank that's already in the tank, and then the vapors coming off the propellant that will provide your blowdown pressure. Hope that wasn't too long-winded. More questions?
So the workhorse nozzle has been run previously, or is this new?
It's new, yeah.
Oh, it's new, okay. So it's not a workhorse yet.
Not yet.
Yeah,
We hope
okay.
to make it one. We put it that way. Yes, we'll put it to work.
Planned to work there, so,
Yeah.
all right.
Well, put it this way, it's not a racehorse.
Yeah.
That was part of the, what drove the name. Any questions? Oh, sorry.
When you're modeling like transient, like start and shut down versus steady state, is it the same code or do you have to do any differences in how you analyze it? Pretty easy to model both.
So, yeah, that's actually, if there were probably one shortcoming to name of our simulation method, that would be the startup right there. So, it would be, it's something that really, what we expect out of our simulation is it'll probably start at a different condition and then converge towards our simulated values.
Cool.
This workhorse nozzle, you said it was film cooled, or that's the plan, the film?
Yes.
It's film cooling. I didn't remember seeing any pictures of how you inject the film into the nozzle.
So the film coolant is injected, there are 52 orifices drilled circumferentially around the fuel manifold, which inject film coolant, I don't remember the exact distance, but essentially right tangential to the wall.
Is that in the combustion chamber or in the nozzle or both?
In the combustion chamber.
Into the combustion.
So it essentially forms like a insulating film
Right.
between the combustion gases.
Actually, we're coming out of the nozzle, that's usually
That's
referred to
the,
as transpiration, we're using just film coolant.
That's the oxidant is used for that?
The fuel is.
The fuel.
Yes, yeah. So it's the orifices are milled straight into the injector, just going straight into the fuel manifold and then spraying fuel.
You would not want to use oxidizers film coolant, I don't think. Anyone else?
Could you speak a little more on the quasi-one-dimensional thermal analysis and chamber conditions, and what makes it quasi-one-dimensional?
Quasi one-dimensional just means that as opposed to being a 3D mesh, that would usually be, if you want like a gradient,
Yeah.
like a full 3D picture of what the chamber's going to look like, it's essentially going to have to be CFD, right? Which you neither have the software nor expertise to do ourselves,
Yeah.
frankly. Quasi one-dimensional essentially means that you treat the free stream gas, so not the boundary layer coolant, but the free stream gas as, you call it roughly uniform across the flow cross section, and then you kind of change as it flows down the axis of the nozzle, right? Using your traditional rocketry 101 equations.
So rather than modeling the entire chamber using complex software, it's more simplified.
It's not anything even remotely approaching a commercial application, so that loss of fidelity is something we deem good enough.
I was gonna ask a little bit more about your injector. How many ports, you described that you have a film coming around the outside. But how many ports actually are mixing the fuel and oxidizer in more toward the center? Was that shown?
Yeah, it's kind of hard to see in this image right here, but do you want to?
So yeah, I can speak on the injector design a little bit. So this workhorse engine specifically uses a very interesting injector design. This was actually someone's master's thesis that went into this. That central orifice there, that's a cavitating venturi orifice. That is the single oxidizer orifice. Impinging around that, right around here, there's a ring of 12 different fuel orifices. That's the totality of fuel for actual combustion. Equally spaced, there's 3 different rings. I think it goes 16, 24, 16 fuel orifices, 24 fuel orifices, and then there's the 50 for battery layer.
Okay, so there's a single oxidizer and then rings of fuel.
Yes.
Okay.
Unlike impinging, so the inner ring of
They
fuel-
don't impinge, they just,
They do impinge.
So-
they do.
Yes.
Yeah, the 12 located right around that cavitating venturi, those impinge on the venturi. The rest of them that are, yeah, so right around there, that's your ring of 12, that's impinging on the cavitating venturi. Then around like here, and around there, and then right against the edge, there's more rings. Those aren't directly tied to combustion. The one all the way far, like out here, that's your battery layer cooling.
That's the cooler. Right. Okay.
And then the intermediary ones replaced there. The reasoning is, the reason behind that was, well, we really don't want the oxidizer to spray onto the walls. And so the idea was that if you add straight post fuel orifices going outwards through the fuel manifold, you'll get more and more fuel rich as you go radially outwards. It was more for safety than actual contributing to combustion, but it is considered to mix within the chamber for our purposes.
I guess it'd be interesting to understand what your real fuel to oxidizer mixture is for the combustion itself. Because you're very fuel rich, it seems like.
Yes, fairly fuel rich. I think our equivalence ratio is, I don't remember off the top of my head. I think the stoichiometric OF is 10.27 for nitrous oxide ethane, and we're running at about an OF of 6 maximum.
What was the stoichiometric?
10.27. You say 10.
Are these dimensions are inches? Or-
Yes.
Yes, sir.
No.
So how long is the run time? It's just a blowdown, right? Because you've got just your, what pressurization you have in your oxidizer and nitrous oxide tank. Is that right?
Yes. Yes. I
How
think-
long is the run time?
So let me run to this slide right here. So these things right here, these are, so because nitrous oxide poses a chemical risk, there's the possibility that it decomposes on its own without any fuel source, which could cause an overpressure event. We use these very small, like just 1 gallon.
Yeah, these are 1 gallon sample tanks.
Right? So our runtime is only on the order of a few seconds. There's also the fact that there are some concerns that when you flow these very high vapor pressure propellants, they're going to get very cold, which may actually freeze your valves. So, you may be planning or prepared for a 1.5 second test, but if your fuel tank can support maybe 12 seconds of burn, once you open those valves, if they freeze open, you may have wanted a 1 second test.
You've lost
but
your control.
Right, now you're getting a 12-second test.
Yeah. So given these 1 gallon tanks, how long is your run?
On the order of about 3 seconds, just shy. Fairly short, a little more than the test. Yes, sir.
There was one chart that had a plot that showed oxygen fuel to fuel ratios for, the mixed ratio versus time.
Right.
One said combustion oxygen fuel and the other says total oxygen fuel. Could you explain the difference between what those two mean?
Sure. So for the purposes of combustion, boundary layer coolant is assumed not to mix with the free stream gas, with the lump parameter gas. But it is still coming out of the fuel tank, right? So this is for the purposes of the thermochemistry, the combustion OF, and then this is for the purpose of measuring our propellant consumption, our total. So this is what we consider to be mixing and combusting, and then this includes the boundary layer coolant. Does that make sense?
May have to continue this discussion later, just to get to the next group.
Okay.
So thank our speakers again.